In the last video, we discussed about the types of hybridization, and we discussed one type of hybridization, that is Sp3 hybridization. Now in this video, we will discuss about Sp2 and Sp hybridization. So first let us discuss what is Sp2 hybridization. The second type of hybridization is Sp2 hybridization or trigonal hybridization. Sp2 or trigonal hybridization. Now from the name itself, Sp2 means one s orbital and two p orbitals will overlap or hybridize to form three new hybrid orbitals of equivalent shape and energy, and we call this as Sp2 hybridization or trigonal hybridization. Okay, now as you can see, it is Sp2. So only two p orbitals are used for hybridization and one p orbital is left in its free state, and we call that free p orbital as unhybridized p orbital. So the third p orbital, that is which is free, the free p orbital, that is called unhybridized p orbital. And let's see the shape of Sp2 hybrid orbitals. The shape is trigonal planar, and when we draw the shape, we have this is Sp2 hybrid orbital. Now we have one p orbital that is unhybridized and it is left in its free state. So that p orbital that will lie at right angles to the Sp2 hybrid orbital. So when you draw the unhybridized p orbital, we denote it with a dotted line. And you can see the unhybridized p orbital has both the lobes of equal size because it is not involved in hybridization. It is not involved in the formation of hybrid orbital. Okay, so this dotted line represents unhybridized p orbital. And what is the shape of Sp2 hybrid orbital? Shape is trigonal planar. And bond angle (120°). So you can see the three Sp2 hybrid orbitals, they lie in the same plane, whereas the unhybridized p orbital, they are at right angles to the Sp2 hybrid orbital. So this is the shape of Sp2 hybrid orbital. Now let us see two examples for Sp2 hybridization. The first example is hybridization in ethene. Hybridization in ethene. We know that ethene is an alkene and it contains a double bond, and the formula, the molecular formula of ethene is C2H4. Now when you draw the structure, this is an organic compound, so there is a double bond between two carbon atoms and there are 4 hydrogen atoms in ethene. This is the structure, CH2 double bond CH2. Now let us see how these bonds are formed, and we know that these bonds are, the CH bond is a sigma bond, this CH bond is also a sigma bond, this is sigma, and there is a double bond between two carbon atoms, out of which one is sigma and the other bond is a pi bond. Okay, because we know the single bonds, they are all sigma bonds. Pi bond is formed along with the sigma bond and it is observed in multiple bonds. So if it's a double bond, then one bond is sigma, one bond is pi. If it's a triple bond, one bond is sigma and two bonds are pi bonds. Okay, so in this case we have how many sigma and pi bond in ethene? We have 1, 2, 3, 4, 5. 5 sigma bond and 1 pi bond in ethene molecule. Now let's see the hybridization in ethene molecule. In ethene molecule we have 2 carbon atoms. Okay, so suppose this is carbon number 1 and carbon 2. Both the carbon atom undergoes Sp2 hybridization. So this carbon will undergo Sp2 hybridization. This carbon also undergoes Sp2 hybridization. So we know that if it's Sp2 hybridization means there are 3 hybrid orbitals of equivalent energy and shape. Now out of 3 hybrid orbitals on both the carbon, what will happen? 2 hybrid orbital on each carbon will overlap with half-filled 1s orbital of hydrogen atom to form how many sigma bonds? 4 CH sigma bond. So the Sp2 hybrid orbital on both the carbon will use 2 hybrid orbitals to overlap with half-filled 1s orbital of hydrogen atom and we get 4 CH sigma bond. Now there is one more hybrid orbital left on both carbon. Now these hybrid orbitals, one left on each carbon, will overlap mutually and it results in the formation of a CC sigma bond. So out of 3 hybrid orbitals on each carbon, 2 are used for the formation of a sigma bond with hydrogen and 1 hybrid orbital is used to form a sigma bond with other carbon atom. Okay, so we have total 4 CH sigma bond and 1 CC sigma bond. Now we have an unhybridized p orbital on both the carbon atom. This unhybridized p orbital will overlap sidewise. We know that we have a pi bond also in ethene. So pi bond is formed by sidewise overlapping of orbital. So the unhybridized p orbital on both the carbon atom will overlap sidewise and we get a pi bond. Okay, so I am going to show the hybridization with the help of a diagram in ethene. Now 2 carbon atoms, Sp2 hybrid orbitals we have to show. So this is of the first carbon atom, the Sp2 hybrid orbital of first carbon atom. Now I am going to show the overlapping of CC sigma bond of the second carbon atom. So this is that overlapping. So this is the Sp2 hybrid orbital of the second carbon atom and you can see one hybrid orbital of both carbon is used in the formation of CC sigma bond. Okay, now the other 2 hybrid orbitals will overlap with 1s orbital of hydrogen atom. Half filled 1s orbital of hydrogen atom to form 4 CH sigma bond. Now we have an unhybridized p orbital. So we have to draw that unhybridized p orbital which is at right angles to the Sp2 hybrid orbital. So each carbon we have an unhybridized p orbital. Now this p orbital, unhybridized p orbital will overlap sidewise resulting in the formation of a pi bond. So you can show it like this. This is the pi bond formed. Okay, so the pi bond in ethene is formed by the sidewise overlap of unhybridized p orbital, means the p orbital left in the free state. So this is the hybridization in ethene molecule. Now next example, let's see the hybridization in Bcl3, boron trichloride, or the same can be applied to BF3 also, boron trifluoride. So here I am going to explain with Bcl3. So next is example 2, hybridization in Bcl3, boron trichloride. Now already we have discussed in the shapes when we studied under VSEPR theory that Bcl3 has a trigonal planar shape with 120-degree bond angle. So same applies here, but here the explanation is based on hybridization. Now we know that in Bcl3 the central atom is boron. So boron, we know that the atomic number of boron is 5. So its electronic configuration is 1s2, 2s2, 2p1. When we draw the orbital diagram, 1s, 2s and 2p. 1s2, 2s2, 2p1. Now here the boron atom in Bcl3 undergo Sp2 hybridization, and you can see from here that the S2s orbital is completely filled, whereas we have only one half-filled p orbital. So what will boron atom do during hybridization? That electron, the paired electron in 2s orbital will get unpaired and it is promoted to vacant 2p orbital. Okay, so boron atom will get excited, means in the excited state, boron in excited state. How can you draw the orbital diagram? 1s, the 2s electrons get unpaired and it is shifted to 2p orbital. Now we have 3 half-filled orbitals, that is 1 2s orbital and 2 2p orbital, which will hybridize to form 3 new sp2 hybrid orbitals of equivalent energy and shape. Now what will happen? How is that Bcl3 formed? We know that chlorine, the chlorine atom electronic configuration, chlorine is atomic number 17 and the electronic configuration is neon 3s2 3p5. So if you draw the orbital diagram, this is 3s2 and 3p5, means 1, 2, 3, 4, 5. And you can see there is one half-filled p orbital in chlorine and we have 3 chlorine atoms. So each chlorine will have one half-filled p orbital. So what will happen in the formation of Bcl3 molecule? The 3 sp2 hybridized orbital or the 3 sp2 hybrid orbital on boron atom will overlap with half-filled 3p orbital of chlorine to form 3 Bcl bond, and it's a sigma bond. Okay, so in this case that overlapping of sp2 hybrid orbital is with the 3p half-filled 3p orbital of chlorine, because it is the formation of Bcl3, boron trichloride. So when we draw the diagram, the hybridization diagram, it will be, we have the sp2 hybrid orbitals. Okay, now this is the 3 sp2 hybrid orbitals of boron. Now each orbital will overlap with half-filled 3p orbital of chlorine. This is the 3p orbital of chlorine. Now this will form or overlap with 3p orbital of another chlorine, and this will also overlap with 3p orbital of chlorine. So this is the 3p of chlorine. Okay, so the shape of this molecule is trigonal planar and bond angle is 120 degree. So the same can be applied to BF3 also, but in BF3 that sp2, boron is sp2 hybridized and that sp2 hybrid orbital overlap with 2p half-filled 2p orbital of fluorine, because in fluorine the 2p orbital is half-filled. So with this we complete the sp2 hybridization. We have two examples. One is ethene and hybridization in boron trichloride, or this is also called trigonal hybridization. Okay, the bond angle is 120 degree. Now let's discuss the third type of hybridization involving s and p orbitals. So the third type of hybridization is sp hybridization or hybridization. Sp or linear hybridization. Now from the name itself, Sp hybridization means which are the orbitals involved? One s orbital and one p orbital will hybridize to form two new hybrid orbitals called sp hybrid orbitals. Now you can see only one p orbital is involved in hybridization. We have two free p orbitals left. Okay, only one p orbital is involved. Two p orbitals are left and they are called the unhybridized p orbital. So how many unhybridized p orbital in sp hybridization? There are two unhybridized p orbitals in sp hybridization. Whereas in sp2 hybridization we have only one unhybridized p orbital. Okay. Now the shape of sp hybrid orbital is linear with bond angle 180 degree. So I am going to draw the shape of sp hybrid orbital. It is linear shape. So how will we show? Like this. Okay. And we have two unhybridized p orbitals. And these unhybridized p orbitals, they lie in different plane at right angles to each other and also to the plane of sp hybrid orbitals. Now, so these two are the unhybridized p orbital. And what's the shape of this hybrid orbital, sp hybrid orbital? Linear, and the bond angle 180 degree. Okay. Now let's explain this sp hybridization taking ethine as example. So example 1 is hybridization in ethine. Okay, ethine, the formula, the molecular formula of ethine is C2H2. Now when we write the structure, it is CH triple bond CH. We know that ethine belongs to alkyne and alkynes contain a triple bond. So the structure is CH triple bond CH. And you can see we have CH sigma bond and it's a triple bond between two carbon atoms, which means one bond is sigma and the other two bonds are pi bond. So how many sigma and pi bonds in ethine molecule we have? 3 sigma bond and 2 pi bond. And which are the 3 sigma bond? We have 2 CH sigma bond and 1 CC sigma bond. The pi bond is between two carbon atoms. Okay. Now let's explain the formation of this ethine molecule with the help of hybridization. Now in ethine molecule, each carbon atom will undergo sp hybridization. So what will happen? The sp hybrid orbitals. How many sp hybrid orbitals are formed? 2. 2 sp hybrid orbitals formed they are formed on each carbon atom. Okay, out of 2 hybrid orbitals, 1 hybrid orbital on both the carbon is used to form a sigma bond. How? By overlapping with half filled 1s orbital of hydrogen. So we get 2 CH sigma bond. We have 2 CH sigma bond. Now there is one more hybrid orbital left on each carbon. They will overlap mutually to form CC sigma bond. So there is one CC sigma bond. Now how is the pi bond formed? We have unhybridized p orbital. How many unhybridized p orbital in sp hybridization? 2 unhybridized p orbital. They will overlap sidewise to form 2 pi bonds. Okay, so let us draw the shape of this ethine molecule on the basis of hybridization, or let's show the hybridization in ethine molecule. We know that the shape is linear This is the sp hybrid orbital of one carbon atom. Now this is the sp hybrid orbital of second carbon atom, and you can see here we have the overlapping, that is sigma bond between Cc. Okay, and one of the hybrid orbital will overlap with half-filled 1s orbital of hydrogen to form CH sigma bond. Now we have unhybridized p orbital, two unhybridized p orbital on each carbon. These are the two unhybridized on first carbon. Now this is the unhybridized p orbital on second carbon. Now they will overlap sidewise. So you can show it like this. Like this. It results in the formation of two pi bonds in ethyne molecule. So we can say the shape is linear with bond angle 180 degree. Okay, so this is the hybridization in ethyne molecule. Now next example is the shape of BeF2 molecule, beryllium difluoride. So example 2. Example 2 is hybridization in BeCl2, beryllium chloride, or we can also discuss for beryllium fluoride. Now I am going to discuss for beryllium fluoride. Okay, now here you know beryllium fluoride. We know that in the VSEPR theory we saw that beryllium fluoride has a linear shape with 180 degree bond angle. Now let's discuss the shape of beryllium fluoride on the basis of hybridization. The central atom in BeF2 is beryllium and the atomic number of beryllium is 4. So the electronic configuration is 1s2, 2s2. Now when you draw the orbital diagram, we have 1s2, 2s2. This is 1s, 2s, and also we have 2p orbital in beryllium, but it is vacant. Now what will happen in the formation of BeF2 molecule? The beryllium will get excited, which means the electron, one of the electron present in 2s orbital will get unpaired and it is promoted to vacant 2p orbital. So what will be the configuration of beryllium in excited state? The excited beryllium, how will you show? 1s2, 2s1 and 2p1. Now you can see we have two half-filled orbitals, one s orbital and one p orbital. They will hybridize to form two new sp hybrid orbitals. So we have sp hybrid orbitals, two sp hybrid orbitals present on beryllium atom. Now let's see the electronic configuration of fluorine. Fluorine atomic number is 9. So the configuration is 1s2, 2s2, 2p5. Now 1s2, 2s2, 1, 2, 3, 4, 5. Now you can see there is one half-filled 2p orbital in fluorine. We have two fluorine atoms. So there are two sp hybrid orbitals on beryllium. What will they do? They will overlap with half-filled 2p orbital of two fluorine atoms to form two BeF sigma bonds, and the shape is linear with bond angle 180 degree. So let's draw the shape on the base of hybridization in BeF2. This is the sp hybrid orbital of beryllium. Okay, now sp hybrid orbital both will overlap with half-filled 2p orbital of fluorine. So this is the 2p orbital of fluorine, and this will overlap with half-filled 2p orbital of another fluorine atom. Okay, and what is the shape? Shape is linear with bond angle 180 degree. So this is the hybridization in BeF2. Same way we can explain for BeCl2. Cl2, beryllium chloride. But in beryllium chloride, chlorine atom, the half-filled orbital is not 2p, it is 3p orbital. Okay, so with this we complete that sp hybridization also. So we can say, in a nutshell, we can say that we have three hybridizations, three types of hybridization involving s and p orbital. The first one is sp3, second is sp2, third is sp hybridization. sp3, the shape is tetrahedral with bond angle 109 degree 28 minutes. sp2 is trigonal with 120 degree bond angle, and sp hybridization is linear shape with 180 degree bond angle. Now something more we have to discuss, that is sp3 hybridization is found in single bonded carbon atom. Okay, and sp2 hybridization is found in double bonded carbon atom, and sp3 is found in triple bonded carbon atom, because for sp3 we discussed the hybridization of methane molecule, that carbon was single bonded. So we can say sp3 is found in single bonded carbon atom, and sp2 found in double bonded ethene, and sp is found in triple bonded ethyne. So whenever you see a single bonded carbon atom, the hybridization of that carbon is sp3. If it's a double bonded carbon atom, hybridization is sp2, and triple bonded it is sp. Now next I have written a question on the board, that is, the question is to find out the hybridization of carbon atom, or which hybrid orbitals are used by carbon atoms in the following molecules. The first one is CH3CH3. You can see that here we have a single bond between two carbon atoms. So you number the carbon atoms 1, 2. The hybridization by both the carbon 1 and carbon 2 is same. The hybridization is sp3. Because I told the single bonded carbon atom, they will undergo sp3 hybridization. Now the second question, when you number the carbon atom 1, 2, 3, the first carbon we have a single bond between two carbon atoms. Now second and third carbon we have a double bond. So you can say carbon 1 will undergo sp3 hybridization, whereas carbon 2 and carbon 3 will undergo sp2 hybridization. So this is sp3, this undergoes sp2, and this carbon also undergoes sp2 hybridization. Now the next example is CH3CH2OH 1, 2. Now we have a single bond between two carbon atoms, so both C1 and C2 will undergo sp3 hybridization. Now the next is CH3CHO. The CHO group is aldehyde group, and when we draw the complete structure of aldehyde, it is a C double bond O. You have learned in class 10 about the structure of aldehyde. Now carbon, suppose you number this as 1 and this as 2, then there is a single bond between 1 and 2, which means the first carbon will undergo sp3 hybridization. But you see, between carbon 2 and O, there is a double bond, which shows that this carbon will undergo sp2 hybridization. Okay, now next is CH3COOH, that is a carboxylic acid. This is a functional group, carboxylic acid. When we write the structure of carboxylic acid, we write like this, CH3COOH. Now 1, 2. The first and second carbon we have a single bond. So first carbon we have sp3 hybridization, and you can see a double bond for the second carbon, which means this carbon undergoes sp2 hybridization. Okay, so this is how we write the hybrid orbitals, or hybridization of carbon atoms. So if you see a double bond next to a carbon atom, that carbon will undergo sp2 hybridization. If it's a single bond, it undergoes sp3 hybridization, and if it's a triple bond, they will undergo sp hybridization. So with this, we complete the hybridization, types of hybridization involving s and p orbitals. Thank you.